Okay, let's keep going. So we have a bird appears to float in the air with little or no movement of its wings. Okay, so we have a bird floating in the air, and we know that gravity has to be acting on the bird, but it's stationary, so there must also be a force that's keeping it up. And there is, it's a buoyancy force, or they call it the Bernoulli's principle, where it provides lift because air moves over the wing and under the wing at different speeds. Okay, so we're just going to call it force of lift for this one. Okay, so when I have picture of my bird, I recognize the forces. Now I'm going to do my free body diagram. I'm going to represent the bird by a dot, and we have our force of lift done by the wings, and then we have our force due to gravity. And it's going to be equal and opposite, okay? Because the bird isn't rising or falling, it's stationary, okay? A cable pulls an elevator at a constant speed up the shaft. So we have constant speed. So if my velocity is staying the same, that means my acceleration is 0 because acceleration is a change in velocity. Okay? And when these forces are equal to each other, that means that the object is in equilibrium. And equilibrium can either be constant velocity or 0 velocity, which is a constant velocity. So you can still have motion and be in equilibrium. It just means that you're going in a constant velocity. Okay? So a cable pulls an elevator. So we have our elevator and the cable that's pulling it. And it pulls the elevator at a constant speed up the shaft. So we have force due to tension of that cable, and we have force due to gravity. And so here's the dot that represents my elevator box here. We have force due to tension, and we have force due to gravity. They are equal in length because their magnitudes are the same, they're just in opposite directions, and that's what makes it a constant speed. Now, if this was greater than that one, if this arrow was larger, then that would mean that it's not in equilibrium and an acceleration would be happening. It wouldn't be moving at a constant speed, it would be accelerating up the mine shaft. Okay? A climber suspended from a rope. Okay, so we have the climber. And actually, this climber is going to be more, like I said, suspended. Okay, and so they're not in contact with the wall, and so we have force due to gravity, and then tension of the rope. Force due to gravity, tension from the rope, they're equal and opposite. A wakeboarder being pulled behind a boat. Okay, so we have our wakeboarder, and he's being pulled behind a boat. Okay, and so I'm going to first, let's recognize that we have a force due to gravity, and then we also have tension. Okay, and usually when they're being pulled by the boat, the handle and that rope is usually kind of at an angle to the top of the boat, right? It's not usually horizontal. So let's include that. So we have force due to gravity, we have force of tension, okay? I think that'd be everything. I mean, we're on water, so friction is zero, well, essentially zero. So I don't think we'd include that. So we would have force due to gravity, and then we have tension that's kind of coming up at an angle there. So force due to tension. All right. Normal force. Let's go into more detail about normal force. Anytime objects are in contact, they exert a normal force on each other. So we have the box resting on a table. Okay, so there's our downward force due to gravity, but because it's in equilibrium, its velocity is zero, or it's going at a constant velocity of zero. We must have an equal and opposite force, and so that force is the table pushing back up on the box, and so we call that the normal force. Okay? This is a perpendicular contact force because it's perpendicular to the surface that's pushing back on, right? So like it's perpendicular to that surface that's pushing. Normal force is always perpendicular to that plane of contact, but it doesn't always necessarily equal weight. Like here, normal force was equal and opposite of force due to gravity, and we've said force due to gravity is the weight of the object. So the normal force would equal, magnitude-wise, the weight. But that's not always the case. In this situation, we have someone pulling on a string with 50 newtons of force, okay? But the object is not lifting off the table. It's still stationary. We're just pulling, we're relieving some of that weight, okay? And so what we would look at here is we say, I have my force due to gravity, and then I have a smaller normal force, and then I also have some in the same direction force due to tension of that rope. Now the box is stationary, so this normal force plus the force of the string, that tension, has to equal the weight or the force due to gravity. Okay? So you can see in this situation how the normal force does not equal the weight or the force due to gravity. It would be that weight minus what the string, the tension in the string. Now this can go the other way as well. So instead of relieving some of that weight, we can push down and apply more force in that negative y direction. Okay? So if I'm pushing down, we have our force due to gravity, we have a normal force, and then we also have this force down here. Now the object is not moving, we're not pushing it through the table, so these forces need to cancel out. So if I take that normal force, let's redraw this actually. So here's the dot that's going to represent the box. We have a force due to gravity, and then we also have an applied force. Okay. Force applied. And the box is not moving, so the normal force pushing back has to be both of those, the magnitude of both of those combined. Okay. So it's going to be somewhere. Force normal. So in this situation, the normal force is greater than the weight or the force due to gravity. Let's go into a little more detail of what we mean by a perpendicular force. Okay? if we have this box sitting on a flat surface, so here's the surface and perpendicular to that would be straight up. So my force normal would be there, okay? But what if that contact is at an angle? Our normal force is not straight up because that's not perpendicular. So our normal force would actually be perpendicular to that plane. So that's our force normal. Okay? And then our force due to gravity, though, is still straight down into the earth. Force due to gravity. Okay. And in this situation, those would not be equal, so keep that in mind. Here, our force due to gravity would equal the normal force. All right, so let's do this example together. Luke hands a box that weighs 127 newtons to Darth. Darth weighs 598 newtons and is standing on the Death Star platform. What is the normal force exerted by the platform on Darth? Okay, so we have Darth Vader holding this box. Okay? So we have the force due to gravity, which is the weight of both him and the box. Okay, we're going to say that's our system. Him holding the box is the system. Okay? So I'm going to represent him with a dot. He's standing on the surface there. So we have force due to gravity of Darth Vader, and then we have force due to gravity of the box. And we know what those are. They're given to us. Okay? And so we have to have a normal force because he's not flying up in the air or sinking down into the Death Star. So the magnitude of these two vectors need to equal the normal force pushing back up on it. Okay? Because our net force needs to be 0. Because again, he's stationary. So we would say force due to gravity of Darth Vader plus force due to gravity of the box. So that would be their weights. In this situation, they're going to equal the normal force there. So we would take 598 newtons, and we'd add that to 127 newtons. Okay, so we have 598 plus 127. That would give us 725 newtons is going to be our normal force. Okay, let's check our time here. All right. Can an object continue to accelerate when a force is no longer applied to it? This base idea here is if all the forces acting on the object cancel each other out, they equal 0, or there's absolutely no forces acting on the object, then that would equal 0 as well. And there's no acceleration there. It could be moving at a constant speed, but it cannot be accelerating. Now, as soon as these forces don't cancel each other out, one is greater than the other ones, and we get some overall net force, that means we would have an acceleration. Okay, so that's it for learning target number 1. Let me know if you guys have any questions.